All right, everyone. This week we're just gonna do primarily a couple examples that are related to the Voronoi cell logic. Just like the couple precedents that we looked at this week in lecture, this one, which is more akin to a sort of 2D Voronoi pattern, kind of applied to a surface. There's a variety of ways you can do this, but let's just look at how to get this sort of initial Voronoi 2D patterning on a flat surface first, and then we'll look at ways to kind of project or map it onto a doubly curved surface like this in this example. So the file you're opening it right now is Voronoi projection. Should look like this. Here is a surface that if I hide things, that I lofted between these two curves. But just for now, I'm going to hide those so you can see. Initially, I've made there are 40 points here that I made in advance. So that's going to be our input. Now, due to the Voronoi logic being part of a big part of like meshing algorithms, particularly, you'll see it actually is coming under the mesh tab and triangulation. So you'll see some of its actually sort of cousins. One called the Delaunay mesh, in particular, is the one that is the generator for the Voronoi cells, and so this is why they're kind of in the same family here right now. Okay, so very simply, you can just plop in this first, Voronoi component down here, and you'll find that essentially this maybe the first time on your computers and in the lab, the first time you drop them in, it'll give you actually a funny little warning that looks a bit like this. So the first time you drop in the Voronoi component, you're going to get this warning message, Voronoi overdose. Excessive use of Voronoi diagrams has been associated with creative gland atrophy, loss of critical thought, confused or nonsensical speech, and an inability to get taken seriously, market increase in Pyrrhic victories, temporary euphoria, followed by prolonged self-loathing, vitamin C. What is that word? I actually don't know. C lever deficiency and blurry artistic vision. Okay. Ask your supervisor or your studio instructor if Voronoi is right for you. Yeah. So, I mean, it's a sort of like funny joke based off of like the fact that you can kind of see there the Voronoi diagram is sometimes somewhat overused, sometimes used correctly, sometimes misused, but just be aware of that. Okay. So inputs, points for Voronoi diagram, optional cell radius, bound containment boundary for diagram, and optional base plane. The points we're providing here are obviously need to be linked in using a point component. So right click set multiple, and you can basically sort of boundary select them all. So these are all our points. And as soon as you put these in, you'll see the diagram actually being constructed on this sort of 2D plane. Now, if you wanted to kind of constrain, what those boundaries are, you can actually do that here, which is a empty rectangle parameter. And there are a couple ways you can do this. The sort of simple, easy, lazy way is to just like right click on here, set one rectangle, and actually just like come into the Rhino viewport and just like click it. And once that's put in, then you kind of see that sort of that's the boundary that you've chosen. So you can kind of freehand it, or otherwise, if you're kind of trying to set things up a little bit more structured, I would suggest you kind of draw out that boundary in Rhino, beforehand. So you get something that you can snap to. So you right click, set one rectangle, and just like snap to those corner points, right? So you get some sort of geometry input, at least in terms of controlling what this input is, okay? And that way, at least that's what you're referencing or what you're attaching to. Now, obviously, you can actually just like because this is looking for that rectangle or that sort of boundary, here under geometry rectangle, this is sort of essentially the same thing, you know, except I can just like set it here as its own standalone component and actually be able to like, okay, basically kind of make sure that this is always there, even though like let's say this sort of original geometry that I had that I was sort of snapping to is just like, kind of moved around. Or alternatively, if you actually wanted this to update or kind of maintain the link with it, then it's really simple. Just put in a generic curve component, right? Link your boundary geometry to the curve, and then convert it into the rectangle this way, which you'll see the boundary actually gets updated and moved over. So I can now actually kind of adjust my boundary location, right, using the geometry, as long as it kind of remains, a four-sided, a rectangular curve shape. Then the sort of conversion between components or between data types will kind of work. Okay. A couple different parameters. You'll see, very, very quickly that this is obviously calculated in real time. So as I adjust or move the points around, then the Voronoi diagram also adjusts to kind of reflect those changes in real time. So it's really useful for creating sort of cellular configurations where I'm wanting to kind of vary or adjust the density of points, right, or any sort of situation like that. This optional cell radius, we can try. I'm actually not sure about the scale, but let's see. 0 smaller than 10.0. This is to be larger than 0 for it to work. So this essentially kind of controls the sort of radius around every single point in which the Voronoi cell is drawn. So up you'll see kind of its behavior up to the point where actually some of the lines actually start to intersect, and that's where they stop growing. And you can use this basically kind of as a control to sort of specify or localize the cells. So the ones that are further apart, will always stay under a specific radius, which can be useful if you're trying to isolate some of these further elements. Right, and if you kind of change this radius by clicking here, double clicking here, and let's say doubling this number to 20, then I can basically expand it to kind of cover the whole, almost, right? There's this little edge where it's not quite, almost the whole diagram. Okay. So the output of this you'll see here, polyline curves, right? So it's a series of polyline curves as an output. And a couple different things that you'll see that similar to any of the Lunchbox plugins, it's really typically just like easier, to try to get deconstruct it, right, to get its like points, its vertices, or its edges, its faces, that sort of thing. Let's actually just look really quick and let's bake it. So right click bake, and I'm going to hide this output first so you kind of see the geometry that you're getting. So I'm doing the select last command to just grab those guys. These are the latest, just to take a look at what I'm getting, right? So these are essentially individual closed and joined polygon or polyline outlines, right? They will be straight if they were clear intersections. If you were kind of at the edge or the boundary, then they'll be sort of like a curved line like this, right? You'll have a curved segment over there, right? Just something to keep in mind if you're kind of messing with this radius. If you don't want any of that, just like don't use this, okay? If you're wanting just like purely straight edges or straight sides. Okay, I'm going to turn my, preview geometry back on. So I have like the grasshopper preview. And let me show essentially this sort of plane that we had earlier, okay? So I'm just going to basically project or pull this geometry up into the plane by simply using the project. So I type project, curve, project a curve on through brep. You can actually project along a direction. In this case, a vector, project onto a plane, etc., etc. So there are different like versions of it. These are the curves that we want to project, and the brep that we want to project to is this wavy plane. Okay, so go to geometry and grab a brep, set one brep, link it in, and link that in. So this projection direction, right, essentially is the vector that it projects to, right? And by default, it's set to the z-axis, so 0, 0, 1, as you can see as I hover over it. I will hide this just so you can see, and that's the projected result of the diagram projected onto a doubly curved surface like that. Okay. I'll hide the brep. Hide this as well, just to get it out of the way. Okay. Now, commonly, as you kind of see here, it's not just the diagram itself, but also, especially if you're kind of doing something like this, there's a gap between the cells, right? There's a little bit of an offset between things, right? And so to kind of achieve that, there are two more commonly used ways of doing that. The first one, and we've kind of seen this before, is to just scale it. So if I scale the object off of its own centroids, right? So we'll need to grab all the cells and grab an area component. With the area component, we can get all the area centroids and use that as the scaling center, right? And at this point, I'm going to just like, hide, most of this stuff just to kind of get it out of the way. Okay, so you'll see the last input here is scaling factor. So let's try 0 smaller than 1.00. So link that in. And you'll see this, right? Now this, using the scaling method has its advantages and disadvantages. The sort of advantage is that the sort of offsetting, the distance that it's offset is scalar to the size of the cell itself, right? So in this case, you'll see like the bigger the cell, even if like, okay, we're fixing our scaling factor at, let's say in this case, 0.8. The size of the cell, the larger the size of the cell, the bigger the offset, or the larger the offset distance, right? But in these cases, right, where the center of the diagram was a little bit denser, then, these sort of offsets are basically kind of proportional to the size of the cell itself. So in cases where that's a desirable trait, it can work for you well, meaning that, these sort of gaps do kind of adapt in their logic to the size of the cells themselves, right? So this is a sort of scalar approach. The second approach is actually just by using the simple offset curve sort of component, which is obviously based off of taking all these curves, offsetting them a specific distance, and you'll see here that actually by default they're offsetting outwards instead of offsetting inwards that we want. And typically there are two ways basically to kind of deal with this problem or issue. One way, well, the sort of quick and easy way, right, or the quick and dirty way, is to actually allow yourself to specify a negative number in the slider, a negative range. So 2.00, let's say smaller than 2. 0.00, sorry, actually this -2 to 2.0, which gives you a small slider that goes from -2 to +2, right? Allow you to kind of flip the offset. So you'll see, okay, here, let me highlight that. So that's offsetting outwards up to where it's converging around 0, and then negative sort of offsets inwards, right? Obviously, you'll see, oh, like where it went red, basically means that when I was offsetting it inwards, -2 or 2, there are some cells, especially these smaller cells, that are too small, right, to actually be offset more than -2. So you get some weird stuff going on, essentially, right? So that's these bit when you have a big difference in the size of the cells between like large and small, that's why like this sort of absolute value offsetting might not be so desirable. Now the other, a little bit more permanent way of actually dealing with this is actually to kind of reverse or flip the direction of your curves. So you go to curves, up here, utility, and find this, flip curves, right? Flip curves, and you basically kind of pass this through first, and which kind of reverses the direction of the curves. And by that way, let's make a slider smaller than 4.0. So even if you put in essentially a positive value here, you'll see that it will actually offset in the right direction. But the same thing, the same caveat is still there, that, these sort of, some of these smaller guys, once you kind of offset them too much, like weird things will kind of start to happen. So, just be aware that there is a sort of threshold to how much you can do that. Especially with really short-sided line segments, they start to disappear and converge. And that's actually the main limitation here with this sort of logic. Now there is obviously kind of, this is one extreme based off of like a pure scaling factor. This is the other extreme based off of a pure distance offset, and there's something that's sort of in between, or a logic that's in between, that basically says, oh, you can kind of do something that's maybe based off of like the cell area, right? So, since you can kind of get area calculations off of this, you can find a way to say, oh, maybe the larger the cell, then the bigger the offset. And if you kind of combine that with using the remap numbers component, then there's kind of a way where you can mix and match these sort of strategies, find something sort of in between. Okay, but that's just to kind of show you how that works. The other sort of very simple thing that, if you're kind of looking at these, is that, okay, you have these more rounded, let's say, figures, right? Typically there are two ways of approaching this. The first one is to actually, and let me hide these just so they're not there and so confusing. Okay. The first one is actually to kind of take those cell outlines and redraw them using the interpolate curve. Oh, actually, no, the NURBS curve, this, right? So basically re-grab all those vertices, and because of that, we'll have to go to curve analysis, and here, control points, right? Extract the NURBS control points and knots of a curve, right? So by doing this, this basically grabs all the corners of every single cell, like the control points, every single cell. We basically are retracing with the control point curve, or the NURBS curve, right? And let me move this further out. Okay. Now, this does have a couple of quirks that you can see. And And this is actually a good thing to kind of show you curve degrees, or maybe 4. These are integer sliders, so 0, 1, 2, 3, 4. It should be set to 3 by default, as you can see here, right? And 2 means sort of less. 1 is basically, and there should be no 0 actually. So 1 is essentially the control polygon. 2 is a second degree curve. 3 is a little bit more, softer. 4 is even softer. And if you go higher, eventually it will actually give you a error, because you can't go beyond like how many sides each figure has. So, but this kind of allows you to control how soft the curve is. The other toggle here is whether or not it's periodic. So this requires a Boolean toggle, a true/false Boolean toggle. It's set to false by default, but when I toggle it, then you'll see the sort of edges, the kink that was usually originally connected to the starting corner, basically gets rounded off, right, or closed off. So you can kind of do this, you're going to do this first and then scale it, right, like we were kind of doing before. So if I just like copy this guy over, okay, and the centroids being the same, and because these are all now their sort of own individual NURBS curves, so actually, yeah, it's probably a better idea if we do its own area calculation over here. Do that. Okay, so you'll have this originally, and then this is the scaled version. So you can kind of control how much it scales. But inevitably, you'll still get kind of like at least that sort of first corner that's a little bit sort of weighted or kinked towards that sort of beginning edge, because that's how it started the drawing, and you can kind of tell which corner that is. And it's up to you to decide whether or not that bothers you or not. Yeah, it's just like does it slightly differently. Okay. So this is the method, basically, that's kind of retracing boundaries essentially, and you basically have these sort of parameters that you can kind of work with. So that's another group. The other sort of common version is to, and I can kind of actually use the offset logic to do this. The other common version is actually essentially to fillet it. And what we'll do is go to curve utilities. So there's a fillet curve at parameter, fillet curve at by distance here, and a fillet. What is this? Fillet by radius, I believe. Yeah, fillet sharp corners of curve. And you can try these. I actually don't think the curve at parameter will work in this case, but we can do this. So this is the fillet, the sharp corners of curve, which is just like the normal fillet, and then fillet by distance. And let's forget this one for now. So this guy, just connect that here in the radius. Let's just copy this, copy paste, give it the radius. So you'll see, okay, now the corners the fillet distance of the corners can be controlled. Up to a certain point, like some of these curves will just like collide or basically kind of merge into one another. But you'll see that you get a little bit more, generally more even control over the corners, and even the offsets to a certain degree. So this gives you, a sort of offset diagram that's a little bit closer, like it follows the sides a little bit closer. Your fillets around the corners are a little bit more controlled. Okay, and that's that. All right, so any of these, honestly, you can basically kind of replace this sort of output into the project. So if you do that, I'll hide this and show this, Control Q. So you'll see that this essentially is that diagram projected onto this doubly curved surface that we've hidden but is there. Okay. Now the other method that we should probably try to touch on is actually before projecting it, if we're going to kind of try to work with a 2D version of this, right? So let's say we're taking this, let's say we're taking the scaled version, this one, right? If we bake this, bake, okay, select last, and you know, maybe let's just copy it out here like that, and copy this as well. So I have the 2D pattern that looks like this, right? And let's say I was really kind of trying to wrap it or map it to the sort of 3D surface instead, right? Which would be actually a little bit more like this, right? Then you would say, okay, well, let me try to do basically the flow along surface command. So let's take this guy, make another copy of it to the side, okay? And just to make it easier, rotate it 90 degrees, okay? And we'll move this over just so visually it's a little bit easier to see what's happening. Okay, so this actually needs a plane, so we'll make a planar surface out of it. So make sure your record history is turned on or it's highlighted. It's like a light blue, right? Flow along surface, select objects. I do a sort of boundary crossing selection separately. Enter. I click my base surface and my target surface, right? Okay. And then let's see what happens if I try to move this guy. And make sure you're kind of in the upper sort of vertical orientation. So you're actually moving this thing on the sort of XY plane. Like move this closer. And so you see that guy shifted over. Okay. And so I can actually know that my mapping is actually, in this case, is actually flipped or rotated 90 degrees. So if I kind of adjust, then that adjusts too. You know, it's a sort of a little bit semi more intuitive way of, you know, kind of adjusting things and having it map to the surface like that, right? Now, any of these examples that we've shown, once you have this, you can easily do the trim command, select your coloring objects, so select all these objects, enter, select the object to trim, so select this like that, and so you can get like just the positives, you know, if these are the windows, or actually typically in this I just use the split command, select object to split, so that's surface, enter, cutting objects is all these lines or all these curves, which then splits that surface apart, right? Which then you can also like just specify, oh, you know, this is glass, right? This is a certain color, change object layer, so that's glass. This is maybe metallic. If you offset the surface distance, let's say 1, and solid, make this solid, then it will get, or it should get thickened. I typically do suggest doing this operation separately or in Rhino, simply because, you know, especially offsetting surfaces with this sort of amount of, you know, curve detail can actually be pretty heavy, as you can see. So yeah, that took a little while. Part of it is actually one thing I should note is that before you do a cutout like this, I would suggest that you basically bump up the UV subdivisions in your surface, because you'll get weird stuff like this happen, where the UV subdivision detail in the surface isn't high enough and you get like really weird cutouts. Okay, so let me back up. So instead of having this surface being only having this sort of typical UV subdivision, rebuild it. It originally had only 4 and 5. Like, let's do 40, 40. On the rebuild surface, say OK. And you'll see like the sort of mapping actually gets sort of shifted a little bit. Typically should mean it's a little bit more precise. So let me see. Yeah, the flow along surface command is actually more precise if you have more subdivisions on the sub-target surface, because it basically kind of has more, let's say, address points to map from. Okay, and then let's split it. Split, select objects to split, blah blah. Let's do that. So cut that, right? So you'll see there's much more sort of ISO curves to work with. I'm going to offset the surface, distance 1, solid yes, okay. Then typically this should work a hell of a lot better. Alright, so I did have to wait a couple minutes, a minute or two for that actually to work, but it's a little cleaner, but I'm still getting, weird stuff here, which means that actually probably the issue is with the original curves that were kind of being used to do the cutouts. So honestly, probably in that case, what I would do to get these sort of openings was actually to do a Boolean operation with these as positives, and that would probably be the way I would kind of try something like that. Okay, so that's that basically for working or generating 2D patterns or 2D Voronoi patterns. You can kind of see a variety of situations and how something like that can be employed. Okay.